Okay, so here I am with my continuation of this is my second video in calculus and calculus chapter 5, and we're talking about integration and so here I've got a random squiggle, but it's not a random squiggle anymore. It is the function y equals 10x squared minus x cubed divided by 50. Well, why did I make it that specific one? Well, I wanted to something that had a nice curve, and I wanted it to sort of fit in the screen nicely horizontally and vertically, so that factor of 10 and that factor of 50 are just there to sort of make it fit nice in the computer screen. Okay, so now what I want to do is I want to introduce this idea called Riemann sums, and it relates to what I was doing in the previous video. And I've got these really complicated formulas here. So basically I've replaced my x's with a plus b's, and so now I've sort of got a step function. You guys can pause the video and think about it if you really want to. But what this does is this is doing what I was just saying in my first video, is it's breaking the area under the curve up into a series of rectangular boxes. And so this right there, this is the left Riemann sum. Okay, this is the left Riemann sum because the left corner of the boxes is on the function. So if I take that and zoom in, basically what I'm saying is that I've got my height here is 0.64 and my width is 0.5. So the area of this rectangular box is going to be 0.64 times 0.5, so it's going to be 0.32. So I know the area of that box is 0.32. Now I go up and I find this box, and it's 0.9375 is my y value, and I take 0.9375 and I times it by 0.5. And I get, just 1 second, and I get 0.46875. So then I add 0.46875 to my, to what I have to add up. And I go like that, and I'm not going to keep going like that. But so this is the left Riemann sum because the left corner of the box is on the function, and then the right corner of the box is just kind of hanging out someplace. And so the problem with this sum is you see that this white that's under the curve is I'm undercounting. So there's area that I'm not counting here because my box is too low. And then over in this area here, there's area that I'm not counting because my box is too high. So you kind of hope that on average the boxes that are too low are going to average out the boxes that are too high. But this is just an approximation, and we're going to get into some really much better ways of doing this later. Okay, so that is the left Riemann sum. And so then I turn that off and I go down to here and I turn this one on, and this is my right Riemann sum. That should be R. Okay, so this is my right Riemann sum. So my right hand corner is on the box. And so I start off, and so basically I start here, and I've got 0.9025 and 0.902, well, I start here, all the way down here. Start there, and I get 0 times 0.5, which is 0. Then there I've got 0.9025 times 0.5 is 0.45125. And then here I've got 1.62 times 0.5 gives me 0.81. And I just sort of, so that's the area, that box is 0.81. And I sort of go through and I add them up, and I see what I've got. Okay, well, there's got to be an easier way to do this. Well, there is an easier way to do this. It's called spreadsheets. So I go over to spreadsheets, and here you'll see that this is what I was saying, that the area of the box that goes from 9.5 to 10 in my right Riemann sum is 0. So this box has an area of 0. This box here has an area of 0.45125. This area, this box right here, has an area of 0.81. And so what I've done in my spreadsheet, let me show you what I've done in my spreadsheet. Here I've got my x values. And so I start at 0, and then I add some dx to it each time. So my formula is the previous cell, A2, which is outlined in blue, times G1 times G1 locked in. And what's G1? Well, G1 is my dx. Okay? So here are all my x values, and they just scroll up by whatever factor I put in this. So if I put 0.1 in this, they go up by 0.1. But I want to put 0.5 in there, so they go up by 0.5. What's happening in this video, or what's happening in this cell right here, is I'm taking my function 10x squared minus x cubed divided by 50. So if I go back here, I've got 10x squared minus x cubed divided by 50. 10a1 squared minus a2 cubed divided by 50, where a2 is my x value. And so if I go down, now it's a3. So that's taking my f of x, with this being my x over here. Now I do what I was saying in my previous video, is the area of each box. The area of this box is f of x, which is the height, times dx, which is the width. So the area, dA, is f of x times dx. So in this here, I've got basically just this f of x times my gx times my dx over here. So it finds the area of that little box. Now, Riemann sums, if I want to find the blue sum, I start at 0 and I go 0, 0.51, 9, 9.5. So I start at 0 and I end at 9.5. So here, my left sum, I'm going to sum up this block from 0 to 9.5. And that's going to give me my left sum. Then my right sum, I'm going to start at 0.5. Well, that's not what I wanted to do. I start at 0.5 and I go all the way to 10. So that's my right sum. And in this case, for this example, you're going to see that the left sum and the right sum are the same. And they're 16.625. but I'm still not happy with how accurate that is. So we got computers here, and computers don't care. So let's make this .1. Let's make my dx 0.1, and then let's take these out. Let's copy my formulas, and let's go down a ways. Let's go down to here. So now my right sum, well, this is my left sum. This is my right sum. What I've done is, instead of making boxes every 0.5, I've now made boxes every 0.1. So I'm going to start at C2, and I'm going to go to C101, and I'm going to get 16.665. And then if I just copy that down, it's going to increment it by 1, and I'm going to get so from C3, which is where 0.1 is, up to C102, which is where 10 is. And I find that, again, for this particular one, my right sum and my left sum are the same before. Let me put that back here. Where was that? That would be down here. Let's make it 0.5. And so let's do equals sum of these. I get 16.625. So using a step size of 0.5, I get 16.625. Using a step size of 0.1, I get this number down here, 16.665. Well, what would happen if I made that smaller and smaller and smaller? Well, fortunately, my graphing calculator has something that I can do on it. I can do numerical integration on my calculator. And so what this is saying okay, so basically what it's saying is okay, so this is saying start at 0, plug 0 into this and see what you get. Now move over some really, really incredibly small number, dx. For a computer, say 10 million, 100 million, or 100 millionth rather, some really, really, really small number, 0.000000000000001. So then take what you got when you plugged in 0 and multiply it by that really small number. Now move over to 0 plus that small number and repeat. Now move over to 0 plus 2 times that small number and repeat. And keep going until you get up to 10, and then you can stop. But no, you can't stop. You got to add up all the numbers together. And so the computer just does that really happily. You can see that if I just change this to 9, as soon as I change it to 9, it just gives me my answer. So it doesn't take the computer long to do this at all, because that's what computers are designed for. And so you see that the proper answer to this is 16.6666666. So basically 16 2/3 is if I do let's do one last thing here. Let's do 0 is less than or equal to y is less than or equal to this. And then I say 0 is less than or equal to x is less than or equal to 10. And I graph this and I turn off this. And so the upshot is that the smooth green that I've got, and I could get like a microscope and I could see that these are actual pixels, but the smooth green that I have has an area of 16.66666, or 16 2/3. Okay, that's that video.